By the way, the week after spring break. So we're doing that Le Chatelier's Principal Lab, and we will be in person that week in the lab. So the way that's going to look, if you haven't checked out the lecture schedule, everybody's going to come in on the same day, but we're going to split it up. First hour will be group A, second hour will be the group B people. So make sure you remember what group you're in. I probably need to update the student lab group A, group B sheet, because I remember some people saying their name wasn't on it, and I tried to update it best I could. But check out that lab sheet. It's in the labs folder. Make sure you remember if you're group A, group B. If you're group A, you'll come in the first hour of your lab time. So let's say your lab is Friday at 10 a.m. The group A people will be 10 to 11, and the group B people will be 11 to 12. Okay, so that's how it's going to work. And you will need to print off your Le Chatelier's Principal Lab document and bring that with you so you can take data down. Okay, unless you have like an iPad or something you're going to do it on. But I'll send more on that in an email, because there's no way y'all going to remember all of that. But I'll send a big email towards the end of spring break with some updates like that. But anyways, just watch that video so you're prepared for that lab. Also with the exam, I'm not going to take time to really go through all the details of the exam since I posted the key. But I am seeing some very, very common mistakes on like Lewis structures. Okay. So just look at that exam key if you miss points on those Lewis structures, and let me know if you have any questions on those. A lot of people got them right, which again is kind of why I'm not going to take time to just walk through all of that. But I saw several people do some very similar common things on a few things with those Lewis structures. And when you some people, when you calculated the molar mass, so the very, very last question in the exam, I know this was a week ago. So the question was about bleach, and you had sodium hydroxide, NaOH, and you had to calculate the molar mass of sodium hydroxide. And I saw a lot of people, I'm just going to address this verbally, but I saw a lot of people when you calculated the molar mass, some of your work for NaOH, there was a coefficient of 2 when you balance the equation. You had 2 NaOH. You do not ever need to include the coefficient when you calculate a molar mass. You need to include subscripts to multiply, like to see how many sodiums and how many oxygens and hydrogens when you're calculating molar mass, but you never multiply by the coefficient. Okay, so some of you got 80 grams per mole for the molar mass when it only should have been 40. Okay, and I tried to make a note of that if I saw you do that. But again, all of that's worked out the correct way on the exam key. So that's kind of all I'm going to say about the exam. I'm going to switch over to the iPad now, and we're going to pick right up with the lecture slides. I do want to remind you of a quiz today, quiz 7, and that quiz is on stuff from Tuesday. So nothing we go over today will be on the quiz. I mean, directly. What we go over today is going to be a recap and a reminder, and it's going to include stuff from Tuesday just inherently. It's going to build on it. But everything on the quiz is mainly directly from Tuesday's content. So don't forget that. And then if you have, some of you have lab this afternoon, so I'll be on the Zoom with you guys, some of you this afternoon, and I'll be on Zoom with some of you tomorrow to do the enthalpy lab. I think that's all we have going this week. So where did we end? Okay, I need to scroll down. We ended right here on Tuesday, all right? So find this slide. We're talking about entropy. And just to recap, what did we do on Tuesday? We started talking about energy and how energy is associated with chemical reactions. We talked about how chemical energy is important for us. And then we talked about enthalpy. We said energy and reactions, there's 3 pieces to the puzzle when we're asking this overarching or this big picture question of how do we know if reactions are going to occur or not. We said enthalpy is a piece to the puzzle. Enthalpy is a measure of the energy within chemical bonds that is absorbed or released, right, as the reaction goes. Some reactions are overall release heat, and those are exothermic. Some reactions overall absorb heat, those are endothermic. And then we start talking about the second puzzle piece, entropy, which is a measure of disorder. Okay, and that's what you see here on the slide, measure of disorder. And we can measure disorder a couple different ways. We said one way we can measure it is by looking at the physical state, solids, liquids, or gases. So if you're having a lot of solids and liquids on the reactant side, and then your products are more liquids and gases. You're making things that are more disordered. Gases are more disordered than solids and liquids, so disorder would be increasing. Or we said if you have fewer reactants or fewer moles of reactants on the reactant side, and then you're making more products or more moles of products, then entropy is also increasing. And then vice versa on those things, entropy is decreasing. So we looked at a real example, this reaction right over here, nitrogen and hydrogen. We said we had 4 moles of gas on the reactant side. We have only 2 moles of gas on the product side. Physical state here doesn't matter because everything is a gas. So nothing's changing when it comes to the physical properties. But we have a difference in the number of moles of gas on each side. And we said, therefore, the delta S was negative because disorder is decreasing overall because of that, okay? So that's where we landed. The example your book gives you is a deck of cards, a nicely stacked deck of cards. Everything is ordered. And then if you scatter them about, we said that, well, here it just shows you entropy increases. So that'd be a positive delta S. So any process like that where things are becoming more disordered, entropy disorder is increasing. Okay, so we're going to move on. We're going to do some practice problems on this. We also looked at units of delta S. So I have those listed right here. Remember, it's calories per mole Kelvin. And we said those are different than enthalpy, which is just kcal per mole. Okay, so we listed out those differences on the units. And those will matter a little bit more today when we do some more practice problems when we get to Gibbs free energy. So here's the question that I want us to look at. I'm going to launch a poll question in just a minute, but we're going to work the first one together. It says, what is entropy? Does entropy increase or decrease? And so then what's the sign on delta S? If it's increasing, delta S is positive. If entropy is decreasing, delta S is negative. And remember, it's a measure of disorder, not of order. So just ask yourself, are things becoming more disordered? Delta S is positive. Are things becoming less disordered? Delta S negative. So the first one here, what do we have? We've got, anybody know what the name of this is? NaHCO3. HCO3 is a polyatomic, right? One that's physiologically important too. So sodium bicarbonate is what you should have thought or said. So we got sodium bicarbonate is a solid. And then we just have 2 moles of it. Okay, I got a coefficient of 2. And then on the product side, we've got sodium carbonate, that's a solid as well, liquid water, and carbon dioxide gas. And everything looks like it's balanced. So you don't have to change any coefficients or numbers there. Just go with what you have. So I've got solid on the reactant side and solid only. And then we got solid, liquid, and gas. If you scroll back up to this figure, we said gases are the most disordered. But liquids are also more disordered than solids. And so inherently, because I'm making things that are gases and liquids here, I'm becoming more disordered on the product side. So delta S here is, disorder is increasing. So delta S for this one is positive. Okay. Plus, I only have 1 reactant and I have a total of 3 different products. Okay, so I'm making more things. This is like a decomposition reaction. So there's 2 reasons, there's many reasons why this one, the disorder is increasing here. Does that make sense? You give me a thumbs up or a thumbs down? Okay, good deal. So I'm going to launch a poll question. I want you to apply the same kind of thinking and reasoning and answer numbers 2 and 3. Start looking at numbers 2 and 3. So the question is just put in the sign of delta S. Is it positive or negative for numbers 2 and numbers 3? All right, give you about 20 more seconds. All right, I don't see the numbers really going up anymore, so we're still missing a few votes, but I'm gonna shut it off. Share results. Okay, so we have number 2. The most popular answer was that delta S is negative, but several people picked that delta S was positive. So I'm glad we're walking through this. Here's what I noticed about number 2. We've got gas and gas. All of our reactants are gas, and this is the most disordered you can be, right? We've got 3 moles of gas here. So I'm just going to write that out, 3 moles, and it's all in the physical state of a gas. And on the product side, I have gas and liquid. Okay, so I only have 1 mole of something that is a gas, and I have 2 moles of something that is a liquid. So the number of moles of stuff adds up to 3 on both sides. So we can't say we're going fewer moles to more moles or anything like that, but the physical state is what I'm really honing in on here. Everything's a gas on the reactant side, but only 1 mole of stuff is a gas on the product side. And then the other 2 are liquid, and we know liquids are more ordered. So we're becoming more ordered and less disordered. Okay, again, I know this is kind of feels backwards because we're measuring disorder, not order, but we're becoming less disordered, in other words, more ordered. So delta S should be negative here. It's decreasing. If you're becoming more ordered, delta S is negative. So the majority of the class picked that, but if you didn't pick that, just know that's why it's negative. Questions on that? Anybody had a question on that? Maybe anybody who picked positive? Does that make sense, I hope?
So you said the liquid is less disordered?
Yes, it's more ordered. The molecules are closer together in a liquid. They don't have as much freedom as they do in a gas, and they're moving with less energy. Okay, so that's why we say they're more ordered in a sense, because gas particles are just flying out everywhere like crazy. We have no control over them. Okay, they're like the kid at the grocery store. You see, they have no control over their children. That's gas particle. That's gas molecules. Okay, not ordered at all. All right, the last one, if you're paying attention at all, 5 minutes ago, we actually talked about this reaction, okay? So everything's a gas in this one as well, but we have 4 moles of gas total on the product or reactant side. We only have 2 moles of gas total on the product side. So again, this is less disordered. So disorder is decreasing. So this is negative as well, negative delta S. So you should have picked negative for both. Okay. All right. Let's keep going. That's it for entropy, by the way. So hopefully after this, again, there will be some more practice problems I post, like when I recommend problems from the textbook. But hopefully you at least have a few of the basics down on entropy. And so we've talked about entropy and enthalpy now. Now we're going to put the 2 pieces together and talk about the third and final piece, which is Gibbs free energy. So let's kind of do a little review on what we've learned about the signs of these things so far. And I'm looking in the chat right now. Bailey says, so less disordered is the same thing as more ordered. That's correct. But I want you to think of it in terms of disorder because delta S is a measure of disorder. So if you're becoming less disordered, you're decreasing in disorder, negative delta S. If you're becoming more disordered, you're increasing in disorder, that's positive delta S. All right, so recap on the signs of these things and what's favorable and what's not favorable, or in other words, what's spontaneous and what's non-spontaneous. So if we remember have a negative delta H, negative exothermic reaction, that is favorable. Why? Because exothermic reactions release energy that can be used for useful work or other driving chemical reactions or other things in the human body. Okay, That's why it's useful. They release energy, they release heat, things that are useful for the human body. So the negative exothermic reactions are what's favorable when it comes to delta H. We said positive delta S increasing in disorder is what's favorable for reactions when it comes to entropy. Okay, so opposite signs here. This reaction will be always favorable. Always favorable or always spontaneous, okay? When you have these two different signs on your enthalpy and entropy. Okay, on the flip side, if you have an endothermic reaction, that's a positive delta H and a negative delta S, that's going to be always or I should say, I'm going to say unfavorable since we're using the word favorable, or non-spontaneous. Okay. So again, if I ask you a question like, is a reaction favorable? Here's your delta S and here's your delta H. Well, if you have one of these two scenarios in rows 1 or 2, then you don't even have to do any math. You can just say, okay, it's spontaneous or it's not, based on the signs of these things. But what if you don't have either one of these situations? What if they're both positive, or what if they're both negative? Okay, then we're not entirely sure until we do some math, until we actually calculate something else that will tell us directly. Okay, so delta H and delta S are indirect ways to figure out if a reaction is going to happen or not. But what we're getting to, Gibbs free energy, is going to be a direct way. We can just look at the sign on delta G and know immediately. We don't have to even think about other stuff. So Gibbs free energy is G, or delta G. Change in Gibbs free energy is delta G. And we have an equation that's going to include delta H and delta S for how we calculate this thing called delta G. Okay, and delta G is a direct way to know, is the reaction going to happen or not. So the equation is this: delta G equals delta H minus, we're going to include a temperature term, temperature times delta S. And I like to put this in brackets or in parentheses because you multiply temperature times your entropy term. So this is your enthalpy. This is a temperature. And this was your entropy. Now, temperature, by the way, is always going to be in Kelvin. Okay? So don't forget how to convert between Celsius and Kelvin. We're going to have to do some of that. Now, I want to go over a few very basic principles of math that you probably learned back in like middle school or junior high. But I just want to remind some people of them because this gets layered and nuanced and a little complicated. But if you remind yourself of these basic things you know about math, it'll help. Okay, we have this big minus sign here. Hold on in the chat. So it's temp times entropy. That's correct, Bradley. I didn't write the multiply sign in there, but you do multiply these by each other. Okay. Okay. If you have well, by the way, positive temperature, Kelvins can never be negative. Okay. You always have to plug in a Kelvin temperature and it can never be negative. So temperature will always be positive. All right. Now, if your delta S is positive, a positive number times a positive number, it's a positive number overall, right? But remember, this negative sign out front is going to make that whole thing negative, right? Because you're subtracting that positive number off, whatever your delta H is. Now, if I know I'm going to have a positive temperature, but if I have a negative delta S, and then I am subtracting overall, a positive times a negative gives you a negative number, right? Positive times a negative is a negative number. And if I'm subtracting a negative number, minus a negative is like you're adding, okay? Minus a negative, you're actually going to add that number, okay? So just remember those things. Remember you have a minus sign out front. Those are just some basic math principles that I wanted to go through. Okay, any questions so far? We're going to scroll to the next slide, which is the table we just filled out plus an added column over here on the right-hand side, which is a delta G column. So what happens is the reason we can always know that a reaction is going to be spontaneous based on the signs of delta H and delta S. If you go plug like if you can use very simple numbers, you could use like -5 and 10 and 2, very simple whole numbers like that. If you plug in a negative delta H and a positive delta S, you're always going to get a negative delta G. Try me on it, okay? It's just always the way it's going to work out. And a negative delta G is what is always spontaneous. We actually have a word for this. I'm going to go down a little bit down here. A negative delta G, I don't want yellow. This is known as an exergonic reaction. So it sounds very similar to exothermic, right? But don't get those two things confused. Remember, exothermic is talking about a negative delta H. Exergonic is your negative delta G. So let's look at this bullet point. Is the reaction you think going to be spontaneous or non-spontaneous? Well, we just said up here, if it's negative, it's always spontaneous, okay? So that reaction will always be spontaneous. It will always happen, very favorable. Energy will always be released overall. Your products are therefore lower in energy, which we said is more stable than your reactants, okay? On the flip side, row 2 from the table, when you have a positive delta G, that reaction is always non-spontaneous, unfavorable, and we have a word for that. We call it endergonic. I think they want you guys to get these confused because they named them almost the exact same as exothermic and endothermic. But it's exergonic and endergonic, okay? So positive delta G is, we call it an endergonic reaction. That is just the opposite here, non-spontaneous. Energy is absorbed overall, not released, and the products are higher in energy, so they're less stable than the reactants, okay? All right, so remember these key terms when it comes to delta G. And then rows 3 and 4, we're actually going to do some practice problems with those scenarios where we do have to plug everything into the equation and see what our delta G is, what it comes out to be. And if it's positive, the reaction's non-spontaneous. If delta G is negative, the reaction is spontaneous. Hey, I like this in the chat. Haley said, just remember, gonic starts with G and Gibbs does too. Easier to keep straight. Look at that. I'm all about little things like that. I'm going to highlight the G. Okay, there. Remember the G. Okay, thank you, Haley. I bet that helped a lot of people. Okay, I'm going to scroll on. We're going to do a practice problem with this now. I know after we talked Tuesday, you guys kept thinking about how ice melts when you take it out of the freezer, okay? I know you were thinking about that reaction and how interesting that was. So we're actually going to work a problem on this now. Ice when it's solid versus ice when it's liquid water. Solid to liquid. So we're given a delta H and a delta S for this equation. And we're going to calculate the delta G. What is delta G for ice melting at 3 different temperatures, -10 degrees Celsius, 0, and +10? Kiara says, can you scroll back up after this? Well, why don't I go ahead and scroll back up right now? Because once we get into the problem, I want to go straight through it. Very welcome. Okay. We're not actually going to calculate it all 3 times. I'm just going to do it one time to show you, because then you will literally just plug in your new temperature each time, okay? But when you do these problems, number 1, remember, look at the units on your delta H and delta S. They're different, right? We said kcals and then calories, and then one has a temperature term, one doesn't. So, and then our temperatures that were given are all degrees Celsius. And remember I said you can only plug in Kelvin into the delta G equation. So if we're going to solve for delta G, we have to use that equation of delta G equals delta H minus T delta S. So here's our equation. And there's 2 steps, 2 preliminary steps that we have to do, that we always have to do before we just throw things in the equation and throw things into our calculator and solve for it. Number 1, you always have to convert temperature to Kelvin. If you're not given a temperature in Kelvin. If you're given it in Celsius or Fahrenheit, most commonly you'll see Celsius, then you got to convert it to Kelvin. And then number 2, we have to make sure units for delta S and delta H match. Make sure they're either both kilocalories or both calories. What you're going to see me frequently do is I'm going to take delta S and convert calories to kcals. Okay? I just keep it simple. I always do it one way. That way I'm never like, okay, which way do I need to do it? I just always do it this way. Okay, so let's take negative 10 degrees Celsius. That's the first temperature we're given, and let's do this problem step by step. So number 1, we're going to do negative 10 degrees Celsius. How do we convert it to Kelvin? What do we do? What's the number? You guys remember? How do you convert this to Kelvin? How do you take Celsius? Not Jay said 370. Okay, yeah, there we go. Very close, not Jay. 273, okay? Plus 273.15. Don't forget the 0.15, okay? So negative 10 plus this is going to give you 263.15 since that was a negative number. And that's Kelvin now. Secondly, let's convert our delta S. What is our delta S? It is 0.26 calories per mole Kelvin. So how do we convert calories to kcals? How many calories are in a kcal? I'm going to write this up here. How many calories in 1 kcal? You guys remember?
Thousand.
Yep, thank you, Keyshawn said it too. 1,000. So all I'm going to do is divide by 1,000. I want to cancel calories. I'm going to convert to kcal. And so you do 5.26 divided by 1,000. Essentially, you're going to move the decimal place 3 places to the left. Or you can put it in your calculator too. So you should get 0.00526. Now, calories canceled, so it's kcal per mole Kelvin. Okay, now we're just going to plug it all in the equation. So our delta H, by the way, was right up here, 1.44. We have not converted that, so we're just going to use that number as is. So delta G is going to be equal to 1.44 kcal per mole. There's our delta H, and then it's minus T delta S. And remember, I like to put all this in brackets, so our temperature is right here, 263.15 K, and we're going to multiply this by our delta S, which is the 0.00526 kcal mole Kelvin on bottom. Keegan, I am lost, okay? Which part, were you good with steps 1 and 2, converting the temperature to Kelvin and converting the delta S to kcal, or do we need to go back further? Lost you on 2. All right, step number 2. All we're doing here is we're making sure that our units for delta S and delta H match. I'm gonna zoom in on these for a second, so if you're writing, I'll zoom back out in a second. You see over here how we got, let me erase. We have kcal on delta H and we have calories on delta S. Those don't match. So if we're going to do addition and subtraction, that's like adding grams and milligrams. You can't do that. You've got to make it both kcal or both calories. That's why we wrote this relationship out right here. And so when we come down here to number 2, we just write out our delta S. There's calories. And I used that relationship that I have highlighted right up here, and I plugged it in, and I put the calories on bottom. So I'm just converting from calories to K. The mole Kelvin part stays with us. That doesn't, we don't, that's not affected in any way. So we just carry those over to the new units as well. All right. So we just did the 5.26, which is our value for delta S. But in kcals, it's 0.00526. So we just divided that number by 1,000 because there's 1,000 calories in 1 kilocalorie. Does that help, Keegan? A little bit? We're going to do more than one practice problem on this. So that was step 2. Then all we did is we took our equation. I'm going to highlight it in blue right here. This was our equation, okay? And we came down here and we plugged in. This was our delta H, okay? That number right up here with the units. I plugged that in, and then I did the minus, just like in my equation. There's the minus, and then I plugged in my temperature. So there's my T part, and then I did times because it's multiplied by delta S, and here's my delta S part. So I'm just plugging each piece into the equation overall, okay? And now we're going to solve for it. So maybe some of you that have actually plugged this in your calculator, you can put it all in at once if you want, but again, make sure I use parentheses properly. Do 263.15 times 0.00526. And then you do the 1.44 minus that, the product of that number. Okay, so Haley said she got 0.055831. So let's round to 0.056. Allie said she got that as well. So it seems to be that the answer is 0.056. And the units on that are what? What are the units here? I see that Kelvin on my temperature and Kelvin on here cancel because I have it top and bottom. But then I'm just adding and subtracting. So yes, Allie, the units are kcal per mole. None of that other stuff, none of this cancels. So that's the units on our final answer. Okay. These problems, like the individual steps and the addition and the multiplication, like, again, I think commonly with chemistry, it's not that each individual step is crazy hard. It's the combination of all this. There's many, many, many steps, and you got to get all of them right in order to get the whole thing right. That's why these problems are hard. Okay, this is some of the hardest stuff we're going to do in chapter 7. So that's an example of one. Now, again, we didn't even work the problem with 0 degrees Celsius or 10. All you would do there for those, I'm kind of out of space on this slide. You would just convert that to Kelvin temperatures, and you would literally do all the same numbers, same delta H, same delta S. You're just plugging in a different number for T, for temperature. And then you just recalculate your delta G that way, okay? So what do you think would happen to delta G? Right now, delta G is positive. That's a positive number, even though it's very, very close to 0. So that means right now, at negative 10 degrees Celsius, that reaction, ice melting to a liquid, is not spontaneous, not favorable, not going to happen. It's too cold, right? But what do you think would happen as you increase temperature to 0, as you increase it to positive 10 degrees Celsius? Eventually, the temperature is warm enough that it'll push that reaction, push that delta G into the negative zone. And once you got a negative delta G, you got a favorable reaction. Danielle, are the delta H and delta S always given? That's a good question. We're going to work some different examples, okay? Some different scenarios so that you'll get more comfortable, usually, but maybe not always. So once I finish with this portion of the lecture, I bet you won't have that question anymore. Okay, this brings up an interesting scenario though. I want to go back up to the table and label one other thing, because here's what I notice. Both, if you look at your delta H and delta S up here, right, both numbers are positive. What row on our table does that fit with when you have both positive H and positive delta S? That is row 3. Okay, that's this scenario right here. Positive and positive. So we use our equation. Now what's going to happen here, if you did the problem with the 0 degrees Celsius and plugged in the positive 10 degrees Celsius, once you convert that to Kelvin, of course, what you're going to see is eventually your delta G, you'd calculate a negative delta G. So what we learn from scenarios like this is delta G can become negative In other words, your reaction can become spontaneous at higher temperatures. That's kind of what this ice problem teaches us. If we temperature and then the negative and then the positive 10 Celsius temperature, once you convert them to Kelvin, of course, your delta G would eventually become negative. Okay, so when you have a positive delta H and a positive delta S, you tend to have a favorable reaction at higher temperature conditions. And then number 4, scenario 4, when it's negative, negative, opposite. The opposite is true, which is that delta G can become negative at lower temperatures. Okay, you tend to have a favorable reaction the lower the temperature is. Okay, a negative delta G. Okay, let's do another practice problem. Everybody got that written down? Okay. Next problem. We have carbon. It's a solid. We have liquid water. These can react to give us carbon monoxide gas and hydrogen gas. Carbon, solid carbon plus liquid water gives us carbon monoxide gas and hydrogen gas. Question number 1, does entropy increase or decrease? What is delta S doing? Is it positive or negative? What do y'all think? Kendall and Bailey both say positive. Okay, so we've got things that are solid and liquid, very ordered, right? Gases are more disordered, so we're more disordered on the product side, so we got a positive delta S. So it's increasing. Good. All right, question number 2. If delta H is negative 31.3 kcal per mole, so it gives us a value, negative delta H, that's exothermic, releasing heat, releasing energy. And then delta S is a positive 32 calorie per mole Kelvin. Is the reaction spontaneous at 27 degrees Celsius? Is it spontaneous at 27 degrees Celsius? Haley says yes automatically. Why did you say yes so quick? We haven't even calculated anything. She says negative H, positive S. So I wanted to bring this up. I'm glad she popped that answer off so quick because you don't even have to calculate to answer number 2. You can just look at the signs and then go look at your table, right? I'm going to scroll up to the table. We've got a negative and a positive. Negative and positive, what does that correspond to? Well, the table, that is condition or row 1. When you got a negative and a positive, it's always spontaneous, no matter what your temperature is. So we don't have to calculate anything just yet. So we know when we do calculate delta G, it should be negative. So is the reaction? Yes, it is. And then question 3 gets us, of course, what is delta G? So now we're going to plug it in and calculate. So again, remember your 2 steps. Number 1, let's convert temperature to Kelvin. 27 degrees Celsius plus 273.15, 300.15 Kelvin. Also, remember to convert delta S. Okay, so it's 32 calories per mole Kelvin. And how do we convert to kcals? You just divide by 1,000. 1,000 calories. This should be for every 1 kcal. And calories are going to cancel. So when you divide by 1,000, you should get 0.032 kcal per mole. Okay. Let me say right now, if you're just watching me do this on the screen, and you don't have pen in your hand and you're not writing this down on paper, working it out with me, you are doing a great disservice to yourself. Because I promise you're going to have a file response question like this on the exam. And everybody always says, well, it's so easy when you're doing it. And it's not easy when you're doing it by yourself. Okay, so please write this down with us, work it out with us. Don't just watch me do it. All right, now we just plug everything in. Our equation for delta G is right here. So delta G equals delta H, which is negative 31.3 kcal per mole, minus, I put it in parentheses, our temperature, which was the 300.15 Kelvin, times the 0.032 kcal per mole Kelvin. Okay, Allie, is that the answer overall for delta G? 21.7 or so? Anybody else get that? What you need to do is 300.15 times 0.032, and then you'll do negative 31.3 minus that. And then let me know if you get 21.7 for your delta G. I want to say you should get a negative number because we said it's going to be spontaneous. So delta G should be negative. Do you mean? Okay, Allie, double check. Other people are saying they got negative 40.9.
I got negative 40.9, but that was when I just plugged it all in as a whole. I'm using my calculator on my
That's
phone.
fine too. You can plug it all in as a whole.
But if you do the, if I do the one that's kind of bracketed off, it gave me like a 9 point whatever. And then of course, if you actually, no, that would equal 40.9.
31.3 minus 9 or so. Yeah, good. Thank you, Tyler. All right, good deal. So negative 40.9 kcal per mole. All right. Questions so far? That's all right. No worries. No worries. It happens. That's why it's all just practice. Okay, let's work one more. I think these kinds of problems need a lot of practice. Everybody good with this slide? Anybody need me to stay here? All right. So I'll stay there for a minute. We can look at this reaction down below as well. We got CaCO3. It's a solid, calcium carbonate. And we are decomposing directly into two gases. Interesting. Solid straight to gases. Calcium oxide and carbon dioxide gas. And then it gives you the delta G. That's nice. We aren't calculating it this time. Danielle, this is going to answer your question. We aren't given the delta H or the delta S here, but we are still asked some questions about delta G. So delta G is a positive 31 mole or kcal per mole at this temperature, 25 degrees Celsius. So question one is the reaction spontaneous at that temperature? Haley says no. Mackenzie says no. How do you know that? The chart. Okay, the chart will be your best friend. It's a positive delta G. So that is non-spontaneous, okay? All right, so no, not spontaneous. Number two, does the entropy increase or decrease? So in other words, is delta S positive if entropy is increasing, or is it negative, entropy decreasing? Well, look at your states of matter, solid, straight to gas. We know gases are the most disordered. So Kendall said it, delta S is negative here. Disorder is, sorry, no. Disorder is increasing. Disorder is increasing. So we have a positive delta S here, not negative. I just was going what I saw with the chat. Okay, positive delta S. Very disordered on the product side, very ordered on the reactant side. So it should be a positive delta S. Okay, question 3 is the most interesting one on this slide. Do you expect the reaction to be spontaneous at higher temperatures? Do you expect the reaction to be spontaneous at higher temperatures? How in the world do we answer this? Well, let's think about some things. What do we know and what do we not know? I know my equation, delta G. If you don't know, just start somewhere. Just start with the equation. Usually that's a good idea. Minus T delta S. Here's what I know. Let's plug in some positives and negatives. I know my delta G is positive because we're told that, right? It's given to us up there by the reaction. I don't know anything about delta H in this reaction. At least I don't think I do. I know temperature is always a positive number because I told you that. And what do you know about your delta S? We figured that out. We said that's positive too. Now, remember earlier when we talked about those little principles of math, we said we got a big old negative out in front here. So overall, this whole number, whatever we don't know any numbers, but we just know whatever our temperature and our delta S is, since it's positive, this minus sign makes that whole term negative. So for us to still get a positive delta G, that would be like saying, you know, if this, I'm just going to make up a number. If we're subtracting off 10 here, to get a positive answer, this has to be a larger positive number. Our delta H has to be a larger positive number, right? Delta H can't be negative here. It can't, or we don't get a positive delta G. Okay, so for us to get a positive 31, that would like be saying that delta H has to be positive 41, right? Does that make sense? So delta H, it must be a positive number mathematically to get a positive 31, and knowing that we have this minus sign. Okay, are you guys tracking with me so far? Have I done anything crazy? Okay, so now what does this fit? We got positive and positive. Which row of the table does that correspond with? That's number 3, right? Okay, and remember what we wrote up here? We said can become negative at higher temperatures. I'm a little confused. Where did you get those numbers? Bailey, I was just making numbers up. I was just doing a hypothetical to give you an example. We don't have any numbers for delta H and delta S here. But I was just kind of plugging some in so that the principle makes sense as far as does that answer your question, Bailey? Okay. So we said it can become negative at higher temperatures. So let's go back to our question. Where is it? Do you expect the reaction to be spontaneous at higher temperatures? What do you guys think? The larger this temperature number is, the bigger this negative number gets. So to get if we have a positive 10 here, that could, we just make up some numbers. That's like, oh shoot, I'm on highlighter. We could have any combination of numbers, but that could be like a 2 and a 5. Okay, I'm making up numbers here. I don't have these numbers anywhere in my problem. Okay, but what if we crank temperature up to like 20? What if we made it a big high temperature? Okay, now 20 times 5 is a 100, right? Why did we make up numbers? Because I'm trying to prove that this reaction can become spontaneous at higher temperatures. And I'm just doing it with simple whole numbers to illustrate the principle behind the matter. But I think I'm confusing a lot of you, unfortunately. Because I'm trying to answer this question is what I'm trying to do overall. Can it become negative? Can you get a negative delta G? I'm trying to see if my delta G will ever become negative. And at high temperatures, but I have to calculate it a couple of different times with different temperatures if I'm going to see that. Now, does that make sense, Kamaya? I have no idea. I'm trying to read you guys. I'm trying to just read your faces on Zoom. Can you give me like a thumbs up or a thumbs down overall? As a lot of people have the same question Kamaya has. Oh, I'm sorry. I wish we were all in person. This sucks. Okay. Hang with me and maybe this will sort itself out. Positive 41 now times minus 100, is that going to give you a positive or a negative delta G? That's where I'm headed. Negative, okay? In fact, that is a negative 59, I believe, right? Okay, so you see, we started out with a small temperature. We started out and we said the temperature was just a 2. We did 2 times 5 initially, and we had just in the red, we had the negative 10. And then we said if we really crank temperature up, a bigger temperature, and we changed it to 20. We changed it from 2 to 20. 20 is a bigger number than 2. It's a higher temperature. Then we got a larger term here, and when you subtract that still from a positive delta H, we did get a negative delta G. So again, I'm just trying to answer this question. The reaction can become spontaneous at higher temperatures, which is why I made that little label on the table up above from earlier. Okay, I have no idea where you guys are on this. I wish I had a poll question on it, but I don't. Do I need to go over this again, or did what I do make sense to anybody? Anybody want to unmute yourself and like talk with me? It made sense. I get it. It made sense
I'm
slowly.
completely lost.
I'm completely lost. Okay. Yeah. If you're on the flip side of this, please let me know. Okay. So higher temp makes it spontaneous. Yes. We are just talking about row 3 from the table. Sorry, I'm burning hot. Let me turn my space heater off. Okay. This whole question on this slide corresponded to row 3 on the table. Where's the table? Right up here. You will have this. I'll put it on your resources page for the exam. I noticed that it corresponded to my row that's highlighted on the table. Okay, this one right here, row 3, because I determined that we had a positive delta S and we also had a positive delta H. Okay, I deduced that I figured out we had a positive delta H when I walked through this stuff right here initially, and I was plugging in my positives and my negatives. I know that temperature always has to be positive. I know that delta S was positive because we figured that out when we answered question 2 from looking at the states of matter, solid, gas, and gas. So I said, if my delta G is positive, it must mean that I have to have a positive delta. There's no way I can get a positive answer here if I'm subtracting numbers and my delta H isn't positive. It has to be positive. Okay, so then I made up silly numbers to prove that if I get a positive 31, which is what I was given, how that had to work out. And then I just changed the temperature and I recalculated my delta G to see that it could become negative if I had a really big temperature here. But I made up hypothetical numbers to do that. So I encourage you, if you ever want to, if you're asked a question like this, plug in simple whole numbers like 10 and 2 and 5, and then change one and see what happens. That's all I did, okay? All right. I'm gonna let you guys process on this a little bit, but if you have any questions, if this just flew over your head, please send me a personal email so I can talk with you directly about it. Okay? I want to do that. I don't want to leave anybody hanging.
I have a question.
Like, yeah,
Will that always be yes?
Bailey.
Can you hear me okay? I don't.
Mhm.
Okay, will that always be yes, that it will become spontaneous at higher temperatures?
Only if you're dealing with scenario 3 from the table, where both your delta H and your delta S are both positive. Remember, we labeled, if you figure out you've got something that looks like scenario 4 here, where they're negative, negative, it becomes the delta G will be spontaneous at lower temperature conditions.
Okay. Okay,
Yeah,
that's
great.
making more sense to me now.
Okay, good.
Yes, thank
All
you.
right. Again, a lot of this is kind of in our heads, and sometimes when we just do numbers in our heads, that gets confusing. So I think writing it out on paper always helps a little more. But all right, I'm gonna move on from this. But again, if you are not ready to move on from this, let's talk further about it. I don't know why I had a blank slide here. I think I meant to do all that in a blank slide, but I didn't. So I'm gonna skip over that. Okay, one more problem. And for you visual learners, this one even has a picture, okay? And then that's gonna be it for Gibbs free energy. We have a very generalized generic equation this time. A, B, and C, okay? A is a solid, B is a solid, C is a gas. And here I'm gonna zoom in over here. We got a little key. A is the green, B is the faded green. So these are the B. These are molecules of A. And these little gold spheres up here, that's C. And those are a gas. So gas, solid, solid. All right. And you're given the delta H this time. How nice. We don't have to figure out what delta H is. It's a negative 23.5 kcal per mole. Okay, now with all that information, question number 1, what is the sign on delta S? What do you guys think? Okay, I'm seeing some in the chat. People are saying positive. So you're going from something that is ordered. Solids are also ordered, but gases are disordered, right? So because we're making something that's a gas here, and notice too, I've got one thing that's a reactant, and then I've got two products. So I'm becoming more disordered in the sense that I'm like decomposing here. We said decomposition reactions are more, delta S is positive. So yeah, I agree. Delta S is positive. Positive delta S. Okay, here's one of our favorite kinds of questions. Is the reaction spontaneous at all temperatures, some temperatures, or no temperatures? Haley in the chat says all. Okay. Kamaya says all. Kishan says all. How are we figuring this out? How do we know? They didn't calculate anything. The chart, row 1 on the chart. Look what we have. We have condition 1 from the chart where we've got a negative delta H and a positive delta S. And mathematically, no matter what numbers you plug in, that will always give you a negative delta G. Okay, good. I think it's clicking now. Okay. All right, any questions before we put a pin in this and move on to reaction rates? So the question there is all temps, or the answer, sorry. Bradley, so wait, so how did you determine the delta S? I would love to hear from a student. Anybody who feels confident answering that? Want to unmute yourself and join the convo? Anybody who knew delta S was positive, how did you know?
So when you get more disordered on the right side, so your product side, then like if you think more disordered, so like you're getting more, then it's positive. And anytime you go from like solid to gas or like solid to liquid, then it's going to be more disordered because the little molecules are everywhere. But if it was the other way around, going liquid to solid, then it would be less disordered because they're all coming together. So then that would make the delta S negative.
Beautiful, beautiful. Can we hit round of applause? Thank you, Haley. Very good. All right. Okay. Did that help, Bradley? Okay, good deal. Good job. All right, reaction rates. So this is kind of the next big topic in chapter 7. We're coming close on time here. So again, we'll finish with reaction rates. And look at that. Look at the encouragement. I love it. We'll finish with rates, and then I'm going to post a video on equilibrium, and I'll post a video on Le Chatelier's principle. All right, rates. Here's the beautiful part. Delta G tells us if a reaction will happen, but it doesn't tell us anything about how fast. So I want to think about the human body for a second. When you eat a meal, how soon do you get hungry again? Some of you are like, it depends on what the meal is, okay? I ain't drinking no Slurpee or slushy and gonna stay full all day. Some of you do that. A meal replacement shake, I don't believe in those, okay? I can't do that. But usually 3 to 4 hours, 4 to 5 hours, okay? If it's a small meal, maybe sooner, right? But that's because our bodies are constantly then doing all these reactions to break down the food we gave it to extract the energy. And those things happen relatively quick. Keegan says like 10 minutes. Are you eating a gulp of air? Is that what you're doing, Keegan? Okay, so the point I'm trying to make is that things happen quickly, usually in the body, because we need them to be broken down quickly. We need them to be circulated quickly. Okay, I bet you could think of other reactions that happen very slowly. Okay, like the decomposition of things out in nature. If a tree gets cut down and it's just chilling there on the ground, it takes a long time for it to decompose, right? So reactions happen at different rates, but when it comes to physiologically, we need them to happen sometimes really decently fast. Okay, that's where reaction rates, that's why they're important. The rate or the speed of a reaction is determined by what? It's determined by how molecules collide. Okay, when molecules collide, that's when we get a reaction. So they have to be this word efficient here. Efficient collisions. Oops. Efficient collisions. So what does it mean to have an efficient collision? Well, the molecules have to hit the right way at the right angle, and they have to hit with enough energy. All right. If they don't hit with enough energy, then they're not going to react. So they have to have correct orientation and sufficient energy to produce a reaction. Okay. The example in this picture down here is with a molecule of ozone. Everybody know the ozone layer in the atmosphere? It's made up of these molecules right here, O3. I think you had a question about this on a homework assignment. That was actually a tricky one. O3. And if that bumps into a molecule of nitrogen monoxide, NO, you can actually decompose the ozone layer this way. And if the nitrogen is the atom that bumps the ozone, then you'll get the reaction, okay? Here it shows it all connected. And then you break down the ozone layer, make all oxygen and nitrogen dioxide. But if the nitrogen monoxide molecule is flipped around and the oxygen atom is the one who hits ozone, you get no reaction, okay? So that's a very real example. I know that's we never think about things like that because we don't have to, because molecules hit no matter what. But that's an example when I'm talking about correct orientation. They have to be facing the right way. Now, the sufficient energy part, I'm going to explain a little bit more with something called a reaction diagram. So I want you to draw this out with me. You are going to have to either draw or label or pull information out of reaction diagrams on the exam. So draw this with me. Oh, Kai says, can you go back up? Good deal. Okay, so we got energy. This is going to actually be, well, I'm just going to write energy. This is talking about Gibbs free energy though. So I'm going to put G for Gibbs free energy. And then we're going to talk about reaction. We're going to label this reaction progress on the x-axis. So we got energy on the y-axis and then the progress of the reaction on the x-axis. So we know every reaction starts out with reactants. That's the first thing. So let's say we have some reactants. It's going to look very similar to what I drew an example of on Tuesday, just a little more detailed. So let's say we have some reactants here and they have this amount of energy. Okay. And then we're going to end up with some products that are more stable. We're going to give off some energy. But in between this, we have some more info. It's more of the story that I didn't tell you on Tuesday. So to have molecules that hit with enough energy, the reason they have to hit with enough energy is because there's actually an energy barrier. And we call it the activation energy. Maybe you've heard this word before in like a previous chemistry class. But they actually have to kind of climb this energy barrier if they're going to react, and they have to clear that quantity of energy, and then they can go on and make the products. Okay. So there's an energy barrier to every reaction. That's usually accomplished when they hit efficiently with enough energy, and they'll clear the energy barrier. So we can label this. The peak of this graph corresponds to that amount of energy, right? And the reactants corresponds to that amount of energy. And the difference between the two, where the reactants started, how much energy they had when they started versus how much energy they have when they hit and they collide, we call this the activation energy. They have to clear that energy barrier, the activation energy, before they can make the products. Okay, so that's EACT, activation energy. Now, the final level of energy, or the final difference in energy between the reactants and the products. You guys love my dotted line here. This is your delta G. This is a change in Gibbs free energy. Right? So here's the deal. I expect you to be able to draw one of these and label these 1, 2, 3, 4 things, okay, on an energy diagram. Not hard, right? Not crazy. You can have wildly different reaction pathways though, okay? For example, everybody good here? Anybody still writing? The one thing I can do with swiftness is draw energy diagrams. Good. Okay, good. All right. You can have reaction diagrams that look all kinds of ways. Here's some examples. You don't always get reactions where the products are lower in energy, like you see here on A. Sometimes, look at B. The products can be higher in energy. But you can still see we can label EACT and delta G on all of these diagrams, okay? So the activation energy, and we're going to fill in some blanks here. It's required to begin a reaction. The efficiency of the collisions determines if you're going to clear that or not. And overall, the size of the activation energy, you can see from A, B, and C here, we got different sizes of activation energy. That determines how fast the reaction is, okay? If you have a very small activation energy, that's going to be a fast or a quicker reaction. If you have a large activation energy, that tends to be a slower reaction. So let me ask you, A, B, or C, which one is our fastest reaction? There we go. Bradley said it, but everybody said it. C, this one's the fastest. Which one's the slowest? Good, Bradley. B. Okay. Which one's favorable? Do we have any reactions here that are favorable and spontaneous? Kendall said C. What are you looking for here? Bradley said A. You're looking for a negative delta G. So in which of these graphs does delta G decrease? And Kendall and Bradley both said it. A, this one is a negative delta G. See, products are lower in energy. That means they're more stable. That's favorable. So this one is favorable. And this one is a negative delta G. C is as well. And that's favorable. Okay. All right. So that's it for reaction diagrams. That's not it for rates though, because there's ways we can alter reaction rates. Let's say we need a reaction to be done at a certain rate, slower or faster. The more you step into the research realm of the world, even with medicine a little bit, you find that we are constantly doing things to manipulate different reactions that we do in the lab. I always felt bad in grad school. I had friends, they have these entire rooms. We call them cold rooms. They're rooms that literally walk in. It's like, like Kroger or Walmart back there in the dairy section. The whole room is cold. Well, people had to literally do their research, like their reactions and stuff in those cold rooms sometimes. And I was so glad that was never me, because I don't like being cold. But we can manipulate rates using 3 different things. Number 1, temperature. So we can increase temperature to make reactions happen faster. We can decrease temperature to make them happen slower. Concentration is concentration of your reactants. That's another thing we can change. What does the word concentration mean, by the way? I actually haven't defined that. We're really going to get into that in chapter 9. But we need to know what it means here. Concentration, like, I don't know, anybody made lemonade at home before? Anybody ever had really bad lemonade? Why is it bad?
It's because it has like a low concentration.
Yeah, it's like flavored water, okay? Like LaCroix, which I happen to really like, okay? So it's just not enough concentration of your, country time powder or however you make it. And that's referring to the concentration, the amount of stuff that's dissolved in the solution. Here we're talking about it with our reactants. So the more reactant molecules you have, the higher the concentration. Lastly, a catalyst. What is a catalyst? Anybody know? Especially there's a biological word that I'm thinking of. Something that speeds a reaction up. There, IJ said it. An enzyme. Okay, enzymes are catalysts in the body. Good. Okay, so if we increase temperature, we're going to increase the frequency. Increase the frequency of collisions. And we're going to increase the forcefulness. okay? If we increase temperature, we're increasing the heat, and heat is a form of energy. So we're literally adding energy to our molecules, okay? When we do that, they're gonna move a lot faster, and then when they hit, they're gonna hit harder, okay? And that, both of those things will increase the rate. Now, again, if we decrease temperature, the opposite things happen. I'm gonna move on to the next slide though. We're running close on time, okay? Okay, increased concentration. There we are increasing the frequency as well. And if you increase, the more reactant molecules you have, that's like, imagine this, imagine you have a reaction the size of an elevator. If you have 2 people in there, they may collide every once in a while. If you have 12 people on an elevator, they're gonna collide all the time, right? Okay. Increased frequency of collisions when you increase the concentration. All right, lastly, a catalyst, like we said, is a substance that increases the rate of a reaction. But in the reaction, it's not a reactant. Okay, it's not part of the reaction, so it is not altered. It helps the reaction, but it's not actually part of the reaction. And it does so, a catalyst lowers the activation energy. That's how it makes the reaction go faster, by lowering the activation energy. And it can do it several different ways. Creating an entirely different pathway. So we're going to draw out 2 different pathways, one with and one without a catalyst. It can just hold the molecules in place and like kind of force them together. It's like when you and your sibling, did something to each other. As me and your mom made you like kiss or hold hands for 10 minutes, force them together, okay? Or just brings them close together and it gives them a chance to react the way they need to, all right? Okay. So let's draw a reaction pathway with no catalyst. Let's say we have reactants here and we got this activation energy in these products, reactants, products. And let's draw in a different color. Some of you have a whole pack of gel pens and you've just been waiting for me to use different colors. If you add a catalyst, you got same level of reactant energy starting out. And that's how it would lower the activation energy. So this blue would be with catalyst. This red, I'm gonna zoom in, is no catalyst. Okay, so we can see that the blue here, this is the smaller ACT, and the red is the larger. Right. So if I gave you 2 pathways like this that were not labeled, said which one has a catalyst, which one doesn't, you could tell me that. Okay. We got 1 minute left. That's it for reaction rates, but don't go yet. Don't go. I've got a poll. I have a poll question to end the day. This kind of is a little bit of a review of delta G stuff. Fill in these blanks here. A reaction with a positive delta G is known as what? Endergonic or exergonic, and is favorable or unfavorable. So let's do this real quick. I know we're at time. We're almost done. This last thing. A reaction with a positive delta G is known as which one? Exergonic or endergonic? And is favorable or unfavorable? All right, 15 more seconds. Just pick one. We're going to go over it. 5, 4, 3. All right, end the poll. There we go. So most people picked endergonic and unfavorable, but a lot of people picked endergonic and favorable. So which one is it? It's the last one, and it's endergonic. Positive delta G is endergonic, and if it's positive delta G, that's not spontaneous. Okay, the negative delta G is